Hello, my friends. Oops. Oh boy, what happened to that? Anyway, the next part of our unit is on springs. All right, springs is a topic we could introduce, we could have introduced when we did dynamics and forces, because springs exert forces on things. However, springs are also able to store energy, and therefore it makes sense to do it here also. So these these things here are supposed to represent springs, all right? And a spring like that has no forces being applied to it has what we call L naught, has what we call a natural length. Every spring has what we call a natural length. Okay? And then by applying, in this case, by hanging a mass from the spring, we get what we call delta x, or how much the spring is displaced from its natural length. All right? Questions are not, or the interesting thing about springs is not how long they are. The interesting thing about springs is how much they are displaced from their natural length. So I'm going to make sure we write that here. Delta x is displacement from natural length. Okay? Now, let's see. And sure, if we hang, well, notice I'm hanging a mass m here, I'm hanging a mass 2m here, and a mass 3m here, and it would be nicer to see it in real life. I'll show you that tomorrow. But what we should notice is that the more mass, two things. The more mass that we hang from this spring, well, if we did a free body diagram for the mass 2m here, there would be a force that I'll call F, what do I want to call it? EL, elastic, and a weight force, right? We'll call this, 2mg. Okay? Well, notice that, this is actually a mistake here. If I go back, that's even better. If I go back to this drawing, notice this delta x is a vector, all right? And the vector points downward. All right, that's a big deal. That delta x is a vector. Just like d and or just like the delta x in the work formula is also a vector, right? So what I want you to notice is, okay, if we go here, here's, well, really, I guess if this is delta x, this is, if you look carefully, it's twice as far, right? And here, and again, I'm going from this natural length. Here's 3 delta x if we hang 3 times as much mass. All right, same sort of thing down here. Here's the natural length, L naught, right? So our displacement here is delta x, this way, right? Here, there's 2 delta x. Here, there's 3 delta x. All right, in the bottom there, let's see. Well, it's the same thing, really, right? We have a weight force downward and an elastic force upward. EL for elastic, like springiness. All right. Big thing to notice, right? Notice these vectors, right? These displacement vectors, both here and here, all point downward, and the force that the spring applies is always upward. So a big deal here. Direction of force, and I should say that this is really important. The spring applies as opposed to the force that's applied to the spring. Okay? The force that the spring applies is always opposite of delta x. Okay? So notice up here, right? The spring is stretched downward. The spring pulls upward. All right? Down here, the spring is pushed downward by gravity. The spring, I don't really mean that at all. What I mean is the spring is compressed this way. the spring pushes back this way. Okay, so that's one big deal. And the magnitude of the force is, well, proportional to delta x. So what we're saying here, notice that in a case like this again, when we stretch the spring 3 times as far, well, that's because we hung 3 times as much mass on it, which means the spring has to apply 3 times as much force back in the opposite direction. All right, so we can put this all into what we call Hooke's law. F-E-L is, well, proportional to x, but there's a constant of proportionality that we call k. Now, you can do this if you want. We make that a vector equation. We put a negative in there, which means this, that the force that the spring applies has to be in the opposite direction of its displacement. Now, I should really do this as, I'm sorry, oh God, I'm just going to clean this whole thing up. What we said is F-E-L is K, I should say delta x. And then if we want to make it a vector equation, we can do that. And K is called the spring constant, or sometimes called the stiffness. Stiffness, that says stiffness. It's measured, if we solve for K, we get F over delta x, which means it's measured in newtons per meter. Right? It's literally, you know, how much force does it take to stretch it a meter? Every spring, based on some characteristics of it, has its own value of K, right? Probably the, you know, the material the spring is made of, the thickness of that material, you know, even some of the properties of the material itself, stuff like that. Okay? Okay. Pardon me for a second while I do this. This leads us to 2 really important graphs that have to do with springs. All right, elongation, right? That really is delta x. All right, and there's force. Well, if they're proportional, we can just say it goes like that. All right, the more force you apply to the spring, sorry, the more you stretch a spring, the more force it applies. That's real important, and a thing that obviously even I still have to remind myself of. It's not about the force that you pull on the spring with. It's about the force that the spring applies. Okay? As we said before, you know, with any graph, one of these 2 things can tell you something. All right? Sometimes they both tell you something. Sometimes only one of them tells you something. Let's see what each tells us here. Well, we know that F is Kx. Now, I'm going to drop the negative here, and in almost every case, you will not use the negative mathematically. The negative just tells us about the direction of the force. All right, so if we just work with what we call Hooke's law, F equals K times X, F-E-L, and I should put a delta in here, I guess. Well, notice the slope is y stuff over x stuff, or force stuff divided by delta x stuff. Oh yeah, that's K, right? Well, that's this. Slope equals stiffness. Right? We could also ideally see that because the slope would be in newtons per meter, right? And those are units of stiffness, or a spring constant. Now the area, and again, what we always mean by area is area between the x-axis and and the curve, in this case, it's a straight curve. This area, we would do as 1/2 base times height, right? Well, which is I'm going to do it like this, 1/2 height times base. Or, let's see, that would be 1/2 of that. 1/2 of f times, well, the base is that, right? Well, this is actually, this part right here is the average force, right? The more you stretch the spring, the more force the spring applies. But if we look at, the force ranges from 0 up to this value. 1/2 of this value is the average force. Well, hopefully you recognize that. That's the work done. Really, the work that we have to do, that I would have to do to stretch the spring this far. Well, that's the same as the potential energy stored in the spring. All right, the other way to look at it is look at the units of the area. The units would have to be these units. Newtons times meters. Well, a Newton meter, by definition, is a joule. So the area has to be, the area is an amount of energy, and it's what we call the potential energy stored in the spring. So we can write this as EPE, elastic potential energy. Well, we can write it as FEL times delta X. Really F average. Well, that average is, let's go back to really this, 1/2 the max. And then how do we write FEL? Well, we write it as K delta X times delta X. Well, that leaves us with our final statement for elastic potential energy. It's 1/2 K delta X squared. Also measured in joules, right? It's an energy. Has to be measured in joules. 1/2 K delta X squared. I'll probably end up writing it as 1/2 Kx squared without the delta. You get the idea. Right? So, let's look at some sort of typical problems with this stuff. Simple spring problems. A 6.5 kilogram ball is hung from a spring with a natural length of 1 meter. The ball hangs in equilibrium when the spring is stretched, blah, 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 blah. Find the spring's constant. Well, guess how we start? Yep, free body diagram. Mg and FEL. It's in equilibrium. That force is 0. FEL minus Mg is 0. FEL equals Mg. What's the spring's constant? Well, that lives in here. Kx. I know, delta x, x, whatever you want. We want K. That's a G. K is, let's call it 65 newtons over x. Now, what's x? X is, by definition, how far it's been stretched from its equilibrium length, from its natural length. X is 0.2 meters. Okay, we don't care about the length of the spring, we care about how much the length changes. So K is, I don't know, I would say something like 6, yeah, 325 newtons per meter. So notice, we stretched it a fifth of a meter, and it took a fifth of, well, that force. It takes 325 newtons to stretch an entire meter. So it's just a kind of simple proportion thing. Uh-oh. An additional identical ball is hung from the spring. Yeah. An additional identical ball is hung from the spring. What's the new length now? Well, if we hang an additional ball, it's going to have the same mass as this one. So now the force is 2 mg. To be in equilibrium, FEL will have to be twice as much, and therefore if FEL is twice as much, then KX has to be twice as much, and that means X just has to be twice as much. Now it's 1.4 meters long. So there's our answer for B. Right? We're just trying to get to that idea that that force applied by the spring and displacement are proportional. Okay? Number 2 here. An archer pulls her bowstring back 40 centimeters by exerting a force that increases uniformly from 0 to 230 newtons. What is the equivalent spring constant of the bow? Well, this, I think we would just go right to FEL is K times X. Well, when it's stretched this far, it takes that much force. So we can just go right to that, 0.4 meters. K is 230 divided by 0.4, 575 newtons per meter. How much work does the archer do in pulling the bow? Here's A, here's B. Well, like we said before, work is change in total energy. In this case, the only kind of energy that changes is EPE. So work is EPE final minus EPE initial. In the beginning, the force is 0, which means it's not stretched at all, which means that thing goes away. So work is 1/2 K X final. Don't forget to square. Oh yeah, we have K. Fine. So 1/2 times 575 times X final, 0.400 meters. Don't forget to square. Times 0.4 squared divided by 2 equals 46 joules. Okay? What do you think? Onward. A good, tough conservation of mechanical energy with springs problem. Okay? Read all you want. What I'll tell you is that there are 3... you pause, read. Good. There are 3 places or 3 instances that you really want to be, well, that may or may not be included in our analysis. Here's place 1. All right? And at this place, I'm saying, let's do this. Let's make a little table. EPE, GPE, KE. And this is at the bottom. All right? When the spring is compressed all the way down. All right? The next instant is when the spring has gone back to natural length, and this thing is just about to come off the spring. It's now doing this. All right, and then there's the third place. Again, the spring is back to its natural length, and the ball is up here. At max height. Okay, those are the 3 instances that we really need to be able to analyze. Okay, so let's just do this little table thing here where, well, if we look at elastic potential energy, Here I would say it's at its maximum. Gravitational potential energy, we could say, is at its minimum, and if we want, if we call this close to it, if we call that height 0, we can even say this is 0. And if it's sitting there on that spring not moving, kinetic energy is 0. Okay? As we go to this second instant, I don't know what you want to call it, middle, and here's top. Well, EPE now is 0. The spring has gone back to its natural length. We'll call this L naught. GPE, well, it's not 0. It's not maximum. It's, I don't know, small. That's the only crappy one. And KE, well, it's going as fast as it's ever going to go. All right, it's been sped up by the expansion of this spring, but the spring is no longer pushing on it. Gravity is just starting to now slow it down, so it's going as fast as it will ever go. At the very top, well, EPE is 0. The spring is not compressed anymore. GPE is at a maximum. At max height, that means kinetic energy is 0. So you can see the energy transformations, I hope you can see, the energy transformations that happen, right? We turn exclusively elastic potential energy into, well, some of each of these, and then that turns all into that. All right, we can use that idea and the fact that if we neglect air resistance and friction in the barrel, that mechanical energy is conserved. Because springs exert a conservative force, not a non-conservative force. Springs do what's the word? Conserve mechanical energy.
Please pardon the interruption.
Pardon the interruption.
Short announcement. Seniors who need school tool access should stop by the TA from 10 to 1 today and tomorrow.
Good.
Seniors can also stop in room 8115 after school today and tomorrow to get their school tool access.
Good.
Thank you.
Okay. I have to actually go to study hall, so this doesn't matter at all to you. I'm going to pause. Again, that doesn't matter to you at all. I'll be back. Just neglect everything I'm saying right now. Yeah. Just wipe that last few seconds out of your memory. So, let's see. Yeah, here's what I want you to do. What I want you to do is solve this problem, okay? And what I'll tell you is it's a conservation of energy problem, just like the ones we solved with roller coasters and watermelons rolling down hills and whatnot, or sliding down hills. Rolling's a whole different thing. But anyway, you're going to start these problems like this. Energy is conserved. Mechanical energy is conserved. Right? We have three terms now. We have GPE initial, we have EPE initial, we have KE initial. We have GPE, PE final, EPE final, and KE final. All right, now, what's initial and what's final? Well, that depends. All right, we said you have three instants that we're really concerned with. All right, that means you can either go initial to final, or initial to final, or initial to final. All right, it's up to you. It really depends on what you know and what you want to know. All right, you can't just arbitrarily pick one. It really is going to, like I said, it's going to depend on what you know and what you want to know. Okay? So, you know, that's how we kind of built this little table down here. It tells us that in each case, you know, what energy is there and what energy isn't there. Okay? You know how to calculate each form of energy. You know how to do GPE. You know how to do EPE. You know how to do KE. All right? So I want you to try to solve this, and we'll have you come back in tomorrow and, well, and see how you did. Okay? This is a great classic problem and good practice right off the bat. Okay? All right, folks. See ya.